Good afternoon, all. Am I audible? Hello.
Yes, ma'am. Good evening.
Okay. Good evening. So let's start the session. This is week 12 sensor and actuator course problem solving session. Um, this is about me. I am ARPITA BISWAS, a student of PhD in electrical engineering from Indian Institute of Technology, Jodhpur. And this is my education background that I did my MTech from IIIT Jabalpur in micro nano electronics, and I did my BTech from Maulana Abul Kalam Azad University of Technology in electronics and communication engineering. And this is more details about me, and this class schedule is Tuesday 7 to 9 p.m. So today actually this is the revision session. We will discuss all the process whatever we are going through in this last 2 to 3 months. So we are going to discuss about this process one by one, and then we will solve some question. So you can unmute yourself and we can discuss the answer. So from the beginning, so from the start, we can start from the cleaning process. Do you know anything about the cleaning process, why it is required, and what there are present some cleaning process, wafer cleaning process? So do you know about it, or have you heard about the clean room? Do you have any idea?
No, ma'am.
Yes, ma'am.
Yes. Have you heard about clean room or cleaning wafer cleaning process?
Yes, ma'am. It's the first and foremost step of manufacturing the sensor.
Okay. And what is clean room?
It is a room which it is a place where we fabricate the sensors.
How?
There are a lot of rooms, clean room, 10,000, lots of rooms.
And how you decide the class, like class 10 or class 100 classroom? Can anyone explain what is classroom? In the wafer cleaning process, we can you have heard about the class 10 or class 100 classroom. When you go for the uh, experiment or the fabricate the devices, in that case we need the classroom. So how any classroom is defined? Actually, micron size particle present in a cubic feet is decide the classroom. Okay, how much particles is present, number which is in micron size in per cubic feet, it decide which classroom it is. Okay, so we are starting from, actually we are starting from the cleaning process, like different type of wafer cleaning process. Then we'll one by one we will recover. Actually this is a revision type session, and then we will go through some of the question of week 12. So first we are going through the simple wafer cleaning process like piranha. So have you heard about the piranha wafer cleaning process?
No, ma'am.
Anyone?
No, ma'am.
Okay, so in piranha is a wafer cleaning process where we add three in the ratio of 3:1, which is H2SO4 and H2O2, and this mixture of solution is used to clean the wafer. So we can dip the wafer into this solution, and the contamination, actually why we need this type of wafer cleaning process, there is some contamination present in the wafer, like if you touch the wafer in bare hand, so some chemical is present in your hand, it can go or it can transfer to the wafer. So when you go for the microfabrication, microfabricate the device, in that case we need proper clean devices, or if there is some contamination is present, then it can defects the result, the output, because you know now the micron size particle is present, the contamination size is micron, and also whatever we want to fabricate the device its size also in micrometer. So it is a little bit hamper our device, or we can't get the proper result. That's why we need the proper cleaning process. So if you want to remove some organic or inorganic type of contamination from the wafer, in that case we are using different type of wafer cleaning process. So first, the piranha is a wafer cleaning process to remove the organic contamination from the wafer. So first, whatever we present this solution 3:1 ratio H2O2 and hydrogen peroxide H2SO4 and H2O2, and in that solution we dip the wafer, and after some time we take out the wafer from this solution, and then we dip the wafer into the DI water. So if actually what is the need of this DI dip into the wafer into this DI water is, if we if we directly after the dip into the solution, the piranha solution, we dry the wafer, then there is some particles of this solution can present in this wafer surface. So it is another type of contamination, like. So if for that case we dip the wafer into the DI water, so the remaining solution whatever is present in the wafer surface, it can goes out. Then after the DI water dip, the wafer is dried into gas. So using the nitrogen gas flow, we can dry the wafer. So this is one type of wafer cleaning process, and there are some other type of wafer cleaning process, like some standard cleaning process are present, like standard cleaning process 1, which is called RCA1, and the second one is the RCA2, which is standard cleaning process 2. So can anyone tell what is the RCA1 and what is RCA2 process? Do you have any idea? Can anyone tell? Please unmute yourself, at least try. Santosh, Ashwin, at least try the cleaning process. Actually today is the last session, so I expect on this is the initial thing now, that why this is sensor and actuator course, and how you at first when we are going to fabricate the device or sensor, then this is the initial stage that we need this wafer cleaning process. So at least try now. Santosh? So RCA1 cleaning process is a standard cleaning process. Why it is required? To remove the organic contamination from the wafer surface, we use the RCA1. And how to prepare this RCA1 solution? So there is a 5:1:1 is the ratio. DI water, H2O2 and NH4OH. So DI water is 5 and the other ratio is 5:1:1. So this we have to prepare this solution in this ratio, and then we have to dip the wafer into this solution, and after that after some time we dip the wafer into the DI water, then using the nitrogen flow we can dry the wafer. So by this process we remove the organic contamination which is present in the wafer. And second process is the RCA2, which is standard cleaning process 2. So why it is required? So for inorganic or metal particle is if present in the wafer surface, so we remove this type of contamination from the surface by using the RCA2 solution. So how to prepare this RCA2 solution? First we have to prepare 6:1:1 ratio, the HCl, H2O2 and hydrogen peroxide. Okay, so HCl, H2O2 and DI water. So HCl is 1, hydrogen peroxide is 1 and DI water is 6. So the ratio is 6:1:1. So by this process we remove the inorganic contamination, and if the metal, some inorganic contamination and metal particle is present in the wafer surface, so we can remove this contamination from the wafer. So this is another type of process. And after that, what is the step? At first, if you want to go for fabricate a piezoelectric pressure sensor or piezoresistive pressure sensor, what we will do, we'll deposit. Actually, the main process is at first deposit the material. Then what process we will flow? The patterning, which is a part of photolithography. Then after that we etch. The main three process is first deposition, then patterning, and then etching. So do you have any idea about the deposition process?
Yes, ma'am.
Can you tell? Can you explain, please? What type of deposition are present? Santosh, have you heard about
Yes,
the
ma'am.
deposition process?
Yes, ma'am. We learned in the previous weeks.
Yes, can you explain? So actually this is the revision type of session, and also we are discuss about some of the question from week 12. So first we will revise this previous things. That's why I am taking this type of question. Then we will go through some 30 question which is taking from this week 12. So this is the initial thing, that some deposition process is there. If you want to deposit some material on the surface of silicon, on silicon dioxide something, or have you heard about the oxidation process or chemical vapor deposition or physical vapor deposition? Take your time and then try
Ma'am,
to.
there are two types of deposition. One is PVD and another one is CVD.
What do you
In physical
understand
vapor
from
deposition,
CVD? What is the full form of CVD?
ma'am, chemical vapor deposition.
Okay, so what do you understand from this? Means the working principle of CVD. How it is work? Do you have any idea?
Ma'am,
So
we use
first
this
we are.
some source.
Hello.
We use some source gas to react on the substrate to grow the product or the substrate, something like that, ma'am. Ma'am, you continue.
Okay. So actually there is a two deposition process are present, mainly chemical vapor deposition and physical vapor deposition. So first we are discussing about the chemical vapor deposition. So there are different type of chemical vapor deposition is present, like atmospheric pressure chemical vapor deposition, second the plasma enhanced chemical vapor deposition, and the third one is low pressure chemical vapor deposition. So and there are also different types of chemical vapor deposition are present. So what is the working principle? Mainly we took the like we are discussing about the atmospheric pressure chemical vapor deposition. So there are three zones. If it is a three zone system, so what happen, we are taking some precursor which is in solid form. Okay, so we put the material source, it is a source material, like we are giving an I am giving an example, like if we want to deposit MOS2, molybdenum sulfide. So what happen in that case, we are taking MO3 precursor which is in solid form, and we are also taking the sulfur. So if it is a atmospheric pressure chemical vapor deposition, this is a three zone system. So if we put in the first zone the sulfur precursor which is in solid form, in the second zone we put the MO3, it is also solid form, and we are also in that case we are set a temperature which is greater or equal to the melting temperature of that material, whatever we want to, because to deposit the MOs2 on the silicon dioxide substrate, we want the sulfur and also the molybdenum oxide MO3. So in that case we are said that the zone temperature, second zone or first zone temperature are equal to or greater than the melting point of that material. So when it heated up now, in that case the material start to evaporate and it start to react, and there also some carrier gas is used, like some argon gas or nitrogen gas, the carrier gas is used. And in that case, using this carrier gas, this after when it is vaporized and it reacts, so and it produces some MOs2. So in that case, this MOs2 using this carrier gas is deposited on the substrate. Okay, this is the working principle of CVD. And the next one is the PVD technique, physical vapor deposition. So there are different type of physical vapor deposition techniques are present. Like the first one is sputtering. I think all of you know about it, the sputtering system. And second one is the thermal evaporation system, and the third one is E-beam evaporation system. So anyone can tell what is sputtering system, what is thermal evaporation, and why we need, and what is E-beam evaporation, how it's work mainly. Take your time, but at least try. What is a sputtering system and how it's work? So in a sputtering system, what happen? It is the when you go for some metal deposition or something oxide deposition. So in that case, we use the sputtering system. So what happen in a sputtering system? There is a target is present, and below this substrate is taken where we want to deposit the material, and also we have to maintain the atmosphere, like we have to maintain the pressure, and we have to give the temperature, yes, the temperature, if we want it to do this in room temperature, so we have to maintain that. And the main thing is the pressure, and also in that case we are flowing the argon, and mainly when the argon flow, it bombarded into the target, and then the target from that and some particles from the target is coming, and it is deposited on the surface. This is the sputtering system. And what happened in the thermal evaporation system? In thermal evaporation system also, there is a boards, like where we take the material whatever we want to deposit in the substrate. So the board, and we should notice that the board melting temperature, it is board means the source melting source holder. So the source holder melting temperature should be greater than the source material. So when we passing some current through this board, and it is heated up, in that case the source material whatever is taking on that board, it is start to evaporate, and it will uniformly deposited on the top where the substrate is taken. Okay, this is also a deposition technique, the PVD technique, the physical vapor deposition. And the third one is the e-beam
Ma'am?
evaporation system. Hello.
Ma'am, why we call the source material called boat?
Actually,
Any reason?
source material, it is not source material, the source holder. So it looks
Okay,
like a
ma'am.
boat. Okay.
Okay, ma'am. Okay, ma'am.
Okay, actually it looks like a boat. In the boat we are taking that source, some material whatever we want to deposit, some gold or some nickel or some aluminium. A source holder where we source means whatever we want to deposit, that is source material, and where we will keep in the boat, and boat is called the source holder. Okay, so next is the e-beam evaporation system. E-beam evaporation system. So what happen in e-beam evaporation? Like in thermal evaporation system, we have to careful about that the melting temperature of the source holder is greater than the melting temperature of the source material. So if it is not happening, in that case what happen? Can anyone tell? Where we are taking the material, the boat melting temperature is, if lower than the melting temperature of the source material, then what happen?
Ma'am, could you repeat the question?
Where we are taking the source material now, this is called boat or the source holder. If the source holder melting, it is also from a metal boat is there. So if the melting temperature of that source holder is lesser than the melting temperature of the source material, then what happen in that case? Think and then tell. Take your time, but at least try. So what happen in that case, if the melting temperature of the source holder is lesser than the source material? So if we are in that case, if we are heating that zone now, so source holder will start to evaporate it. evaporate instead of the source material. But we don't need in that type of environment na. We want whatever the source material we are taking, it will deposit on the surface of the substrate. But if the melting temperature of the source holder is lesser than the melting temperature of the source material, in that case the source holder metal will start to evaporate. So to solve this type of problem, we can go for the e-beam evaporation system. Anyone know about the e-beam evaporation system?
Ma'am, in EB operation, we used a source holder called a crucible.
Yes.
It is very, it is made up of quartz. It is very have high melting point. So we easily rectify the previous issue.
Yes. And what we use to heat this material? Because at first we have to heat this material na, then it will start to deposit. E-beam evaporation. So what happen in that case? Rajiv? Janardhan? So in that case we simply use the e-beam. So e-beam goes to the source material and then it is start to evaporate and it is deposited on the surface of the substrate. Okay. Then we are going to discuss about some lithography process. So if the material is deposited, then we have to do the patterning process. So we go for the photolithography process. So what happen in photolithography process? A design or pattern is transformed from a mask to the material whatever we want to transfer the pattern. So do you have any idea about photolithography process? So first we are going to discuss about the mask. Have you heard about the dark field mask and bright field mask? Santosh?
Yes, ma'am. We heard the word bright field mask and dark field mask.
How to identify it is dark field or bright field? Like if there is a pattern, like if you want to transfer a pattern of the interdigital electrode or a electrode, okay, so the electrode is in dark color or dark shade and the outside or rest of the part is transparent. So what type of mask it is?
Dark field mask.
How it is dark field mask? The pattern is in dark.
Sorry. It is bright field mask.
Yes, the most of the portion is transparent, so it is bright field mask. Okay.
Yes.
And the opposite is dark field mask.
mask.
Okay. And also in that case we use the photoresist. Have you heard about positive and negative photoresist?
Yes, ma'am.
So can you discuss or can you explain? How we can
in positive photoresist, it is able to maintain their size and pattern as a photoresist developer.
okay.
And the solvent doesn't penetrate the areas that have not been exposed to UV light.
It's mean if the covered area is if the you are taking take as example, like if there is a positive photoresist present and the covered area which is covered with the positive photoresist and then UV exposed. Then when we go for the development process, what happens? The covered area will gone or it will remain for positive photoresist.
Ma'am, in positive photoresist, the area which is not exposed by UV light is stronger.
Yes, and what happened for negative photoresist?
It is vice versa. The area which is not exposed by UV light is weaker.
Yes. So we are going to discuss about the photolithography process. So first we have to so what is the first process when you go for the photolithography? Can anyone explain? There is no hurry, you can take your time, but think, when you go for the photolithography process, what is the first process?
Ma'am, I have one doubt, ma'am.
What?
Ma'am, we classified into photoresist into two, positive, negative. How you split these into two, for positive, negative? Any example to explain this?
I did not get you. What is your question?
Ma'am, in photoresist, we divided into two, positive and negative.
Okay.
How we are split into two? I can say in positive photoresist, the area which is not exposed by UV light is stronger. In this way, it is okay. But I want to know how it is how is fabricated. I don't know how to ask this question, but I have a slight doubt on positive and
Okay,
negative photoresist.
I'm
How it
going
can
to
be made?
discuss about the positive negative. I think your doubt will clear. Okay.
Okay, ma'am. Okay, ma'am. We will
So
continue.
what happen in positive photoresist, like if is a pattern, like there is a deposited material, and at first I am going to cover all the area of the photolithography process. So what happened in that photolithography process, we have to deposit. At first there is a deposited material is present, like silicon dioxide or something else. Then we have to transfer a pattern from the mask to that layer. So what we will do, at first we will cover this a surface of that deposited material with photoresist. So how we will define what type of photoresist we will use? Actually, whatever the pattern we are going to achieve na. So because of the application based, whatever the pattern we want, in that case we are using that type of photoresist. So basically there are two types of photoresist is present. So what happen in positive photoresist, like if we are using the positive photoresist in the surface of the deposited material, then if we go for the UV exposed now, in that case the area which is not covered, it means when at first we coated the wafer with the like we are taking the example of positive photoresist. Then what we will do, we will go for the soft bake process, which is 90 degrees centigrade for 1 minute. After that we will UV expose. When UV rays is coming through this mask to this positive photoresist, what happens, the mask pattern is transformed from the mask to the photoresist layer. Then after that we go for the hard bake process, which is 120 degrees centigrade for 1 minute. Then after that we go for the development process. Then what happen in development process, there is a chemical is present. So what happening for the positive photoresist, the like there is a mask and there is the chrome is present. Okay, so if the chrome is present and there is a positive photoresist, so the covered area, it's mean there is the covered area will remain. Okay, the chrome is present and there is a positive photoresist, though this portion will cover, and the transparent area, the UV rays coming na, so it is coming to the positive photoresist. What happen in that case, this positive photoresist become weaker. So when we will dip the wafer into the developing solution, in that case what happen, it will goes out, it means chromium is present, it means it stop the UV rays there na, and the transparent area means it the UV is directly coming to the positive photoresist. So which portion of the positive photoresist is coming to the contact of the UV rays directly? When we dip the wafer into the solution, developing solution, in that case this portion will goes. Okay, this portion will goes. So this is the nature of the positive photoresist. And what happened for the negative photoresist? The area covered, this is the actually the nature of this different type of photoresist. The area covered with this chrome, like this will become weaker, and whatever where the UV ray is directly coming na, it is coming to the contact of the UV rays, the photoresist, this portion will become harder. It means positive photoresist when coming to the contact with the UV ray, when we then after that we dip the wafer into the developing solution, it will goes out. But if the negative photoresist comes contact to the UV rays directly, so it is become more harder, so it will stay. And which portion is the chromium is there na, mask, so which portion is covered with that in so there this portion is not directly coming to the contact with the UV rays, so it will become dissolving into the solution. When we dip the wafer into the solution, developing solution, in that case this portion will gone, but the portion of the photoresist coming the direct contact with the UV rays, it will stay. After that what we do, we do the etching, because the pattern is transforming from the the pattern is transforming from the mask to the photoresist layer. Now what do you want? From the deposited layer to that from the from the UV photoresist to the deposited layer, it will transfer. So how it will transfer? We will follow the etching process. Like if the underlying layer or the deposited layer is chromium or gold, like the gold, so we will etch by the gold etchant. So we will dip the wafer into this etchant solution, and then whatever portion, then what happen when we go for the developing process, some portion the photoresist is remain, some portion the photoresist is gone, according to the nature of the positive or negative photoresist, or the bright, it is dark field mask or the bright field mask. Okay, so in that case some portion after the developing, some portion is the photoresist is remain, some portion is gone. So when we dip the wafer into the etchant solution where the photoresist is not present, in that case, in that portion the etchant will start to work, and it will etch the underlying deposited layer. Okay, so what happened in the next, after etching we will dip the wafer into the IPA or acetone. So IPA acetone is there, it will remove the photoresist, remaining photoresist, some portion the photoresist is present now after the developing process. So what happened in that case, this remaining remaining photoresist is gone. So now it is clear to you, Santosh?
Yes ma'am, yes ma'am.
So can you explain whatever I have, so I can understand how you have any doubt or not? So can you explain? Shubhendu, can you explain this process, whatever I have told? You have gone through the lectures. At least try.
Ma'am, if you use the positive, if you etch the positive photoresist, the UV light is if the UV light is exposed in positive photoresist means the area is weaker. Am I correct?
If the okay, for positive photoresist, whatever portion is coming the direct contact with the UV, so this portion will weaker.
Once again, ma'am.
If it is a positive photoresist, so in positive photoresist the area which is coming direct contact with the UV rays, na, this portion will become it's when we go for the developing, dip the wafer into developing, this portion will go on.
Yes, ma'am. Now I can understand, ma'am.
Okay. So can you tell the wafer fabrication process of a piezoelectric pressure sensor, or what do we understand from a piezoelectric pressure sensor? I think you have gone through these videos. Take your time and then tell, or no hurry.
Ma'am, in piezoelectric pressure sensor, if we strain gauge is used, ma'am, and if you apply the pressure, there is change in voltage. It is called some piezoelectric
Electric sensor.
effect.
Yes. And how to fabricate it? All of you gone through the video lecture of Dr. Hardik J. Pandya, so I think you will be able to answer this question. Take your time, there is no hurry. You have seen na, this type of diaphragm is present, and there is some piezoelectric material is present, and from the back side we etch, and this type of shape is there. So if there is some pressure is or force is going, then according to it, if it is piezo-resistive, the resistance of this material will change, and if it is piezoelectric, then the voltage will change. So how to fabricate this type of devices? Take your time and then try to give the answer. Please at least try. So what present in the piezoelectric pressure sensor? What present? There is a two type of fabrication is needed. One of them is the surface micro machining, and the second one is the bulk micro machining. So when we go for the bulk micro machining, when we etch or something fabrication device we used to etch the bulk portion of this substrate. Okay. And what is called surface, when we go for the microfabrication process on the surface, like there is a two type of micro machining is need, bulk and the surface micro machining. What happen in the surface, the front side, there is a front side like this type of shape is there. So front side, what happened, initially we are taking a silicon substrate. So on that silicon substrate we have to deposit the silicon dioxide. Do you know about the deposition process of silicon dioxide? Have you heard about the oxidation process? Santosh?
Yes, ma'am. About the wafer, always we grow the silicon dioxide to avoid the short of the metal, shorting of metal. Am I
Okay.
right, ma'am?
Yes. So how to grow this silicon dioxide? Oxidation process, like have you heard about dry oxidation and wet oxidation?
Yes, ma'am. I have.
So what is the difference between dry oxidation and wet oxidation process? The word dry and wet, so you can get clue from this, na? Like if you want to deposit or grow the silicon dioxide on silicon, so Si to SiO2, if it is dry oxidation, so what type of gas or precursor we will use? How to grow silicon to silicon dioxide?
Ma'am, it in dry it oxidizes with oxygen.
Yes. And for wet?
It is water vapor.
Yes, water vapor with oxygen. Okay.
Yes, ma'am. Water. Yes, ma'am.
Yes. So after that, if we deposit the some oxidation oxide on the top of the silicon wafer, then we will we will grow some then we will deposit or pattern transfer the ID pattern. So we need an electrode now, so in the front side. So how to now tell me how to deposit the gold. I have already told about the deposition process. Any of the deposition process name?
Yes, ma'am. There are two techniques. You already told physical evaporation and chemical evaporation.
But for gold, which process we will use? Actually, for the gold deposition, we mainly use the PVD system. Okay. So we can use sputtering, we can use E-beam evaporation, and also we can use the thermal evaporation system. So after that we go for the photolithography process, because after the gold deposition, gold is deposited on the wafer surface, then we go for the photolithography. So from the mass to the deposited material, the pattern is transferring, and after the etching and developing all the process, we can get the electrode on the top surface. And after that, if we want a micro heater, in that case also we can deposit some material, but in between the ID pattern and the micro heater, the electrode and the micro heater, we have to deposit the silicon dioxide, because it is stop the shorting, the electrical shorting between the micro heater and that ID pattern or the electrode. So this process we can fabricate the surface, or the surface micro machining is happen for the piezoelectric pressure sensor. But this if we want this type of, like their surface, there is a micro machining or some fabrication step we have done, but in the bulk portion so we have to etch the silicon wafer. So how, now tell me how to etch the silicon wafer, or some wafer if you want to etch, some etching process now we are going to discuss. So do you have heard about the etching and what type of etching process are present?
Ma'am, there are two types: wet etching and dry etching.
So what happen in wet etching and what happen in dry etching?
Ma'am, dipping the substrate into chemical solution is called a wet etching,
Hmm.
and it removes material.
Hmm. And what about dry etching process? Have you heard about DRIE process, deep reactive ion etching?
Yes, ma'am.
So what happened in that case? Some reactive ion etch the material. Okay, so in that case we are not we are using some gas or the reactive ions to etch that material. So in that case it is called dry etching process. And wet chemical etching process is when you use some liquid, when it is in liquid format. Okay.
Okay,
So,
ma'am.
have you heard about isotropic or anisotropic? So, can you tell me what is the difference between the isotropic etching process or the anisotropic etching process? Shubhendu, at least try na. What is the difference between isotropic and anisotropic? So think about this question. I'm coming back in 1 minute. Actually, uh, actually isotropic etching and anisotropic, this is the etching process. Uh, so it is not about Shadin, or actually how it is etching. If it is etching in all direction, then it is called isotropic. But if it is etching in the particular direction, then it is called anisotropic etching. Okay, just a minute, I am reconnecting. Actually there is some internet issue. Just wait for a minute. So what happened for the isotopic etching process, like if there is a device and there is a surface material is present, so if we dip this wafer into the some etchant solution, if it is isotropic now, so in all direction, like here, in all the direction it will etch the wafer same type. Okay, but if it is anisotropic process now, it will in a particular direction it will etch. Like if this is the this is the device or substrate, and there is a mask is present, like if we are putting some photoresist is there, so it can act as a mask layer, or some oxide layer is present, and this is the silicon wafer. So if we dip this wafer into the like we are taking as an example of TIMA, this is the etchant solution, so the silicon is deep into this TIMA solution. So what happen if there is a mask is present or oxide is present, so in a particular direction, like that type of shape there, in a particular, if there is a mask is present, so in a particular direction it will etch. But if it is a, so it is anisotropically etch. But if it is a isotropic etch, so it will this type of shape, it means here the mask is present, so it can goes that way na. So it is not happening in the practical cases, so this type of shape is present, so in that way it will etch. So like in the middle it is etching, and this is the mask is present, so this type of shape is there. But what happen in isotropic etchant, so it can etch in all directions, so that type of shape is present, so mask is present, but in below the material is etched out. But we don't need that type of etching. So depends on the application, we use different type of etching process. So now I think the etching process is clear. If it is isotropic etching process, in that case it will etch in all direction in the same way. But if we want to etch in a particular direction, in that case we go for the anisotropically etch process.
Yes, ma'am. Yes, ma'am.
Okay. So in that process we can fabricate a piezoelectric or piezoresistive pressure sensor, that type of diaphragm we can fabricate using this process. Like the, if we go for the anisotropically wet etching process, in that case this type of shape is present. So when we go for the piezoresistive or piezoelectric pressure sensor, in that case we use this type of wafer fabrication process. So now we are going to start some of the question from the week 12. So at least try, and please unmute yourself and at least try, and you can take your time, there is no hurry. So this is the first question. Properties measured using the ETM. The full form of ETM is the electrical, thermal and mechanical sensor for breast cancer tissue. Phenotyping are: the first option is capacitance, elasticity, specific heat. The second option is resistivity or resistance, elasticity or the thermal conductivity. And the third option is capacitance, viscosity, thermal conductivity. And the fourth option is resistivity or resistance, viscosity or specific heat. So properties, what is the question here? Properties measured using the ETM, electrical, thermal and mechanical sensor for breast cancer tissue. Phenotyping are. So what is the right answer? Please go through the question carefully and take your time, then try to give the answer.
Ma'am, I think it is option B, resistivity, elasticity or thermal conductivity.
Yes, this is the right answer.
Thank you.
Okay. Then the second question is, which material is most preferred for gears made using FDM 3D printing? Take your time and try to give the answer. FDM means the fuse deposition modeling. So which material is most preferred for gears made using the FDM 3D printing? PLA, ABS, nylon and HIPS. If you don't know the answer, this is not the issue, but at least try. This is there are some MCQ question, so we are going to solve this question. It will also help in your exam. Take your time and then try to give the answer.
Ma'am, ABS.
No, it is not ABS.
मैम ऑप्शन ए होगा PLA.
Not really. The right option is nylon. Then the question number 3 is, which web interface is used for a remote 3D printing demonstration in the lecture? The first option is the OctoPI, the second option is the OctoPrint, third option is the Raspberry Pi, and the fourth option is the Arduino. So which web interface is used for a remote 3D printing demonstration in the lecture? Actually this question is directly taken from the lecture video of week 12. which is taught by Professor Hardik J. Pandya. I think you have gone through the lecture. Take your time, but at least
बेसबल
try.
का ही होगा.
Santosh, what is the right answer?
Ma'am, I don't know, ma'am.
Okay. So the right option is option B, octoprint.
Okay, ma'am.
But at least try, na.
Yes, ma'am. Yes, ma'am.
So next question is question number 4. Which 3D printing technology is most similar to an inkjet 2D printer? So the first option is laminated object manufacturing. The second option is the SLA, and the third option is STL, and the fourth option is the material jetting.
SLA.
Actually, these are the 3D printing process. There are 5 types of 3D printing process. So which is similar to 2D printer?
SLA होगा.
Take your time and then try to give the answer. So the right option is material jetting. Next question is the question number 5. Which 3D printing technology is most widely used because of low cost of the machine and maintenance cost actually? The first option is FDM, second option is the stereolithography, the third option is selective laser sintering, and the fourth option is material jetting. Take your time and then try to give the answer. So which 3D printing technology is most widely used because of the low cost of the machine and maintenance? The first option is FDM, The second option is the stereolithography and selective laser sintering, the third option, and the fourth option is material jetting. Hello.
FMD or क्या?
Yes, the right option is the FDM.
हाँ बिल्कुल.
So the next question is which is a water soluble 3D printing material from the following list. The first option is PLA, the second option is the ABS, the third option is the wood filled material, and the fourth option is the PVA. So please go through the question carefully and then try to give the answer. Which is a water soluble 3D printing material from the following list. The first option is the PLA, the second option is the ABS, the third option is the wood filled material, and the fourth option is the PVA. Take your time and then try to give the answer.
PVA.
Yes, the right option is PVA. Good. Next question is which stage is considered as non-invasive breast cancer? First option is the stage 0, then stage 1, stage 2 or stage 3.
Stage 2.
No, stage 0 is called the non-invasive breast cancer.
Okay.
Then which stage? Then just a minute. Okay. Then the next question is which stage is considered an early stage of invasive breast cancer? So the right option is option B, stage 1. And this is the subcategories of the stage 2 breast cancer. So do you know the answer? So stage 2 subcategories are stage 2A and stage 2B. Then the question number 10 is which stage is considered as locally advanced breast cancer? So locally advanced breast cancer is stage 3. Then the next question is stage 3 of the breast cancer are divided into subcategories of dash. Have you gone through the lecture 12 video? Sorry, week 12 videos. So there are 3 types of subcategories present in the stage 3 breast cancer, like stage 3A, B and C, and depending on the size of the tumor. So next question is which stage is considered distinct metastatic cancer, meaning cancer has spread to other organs and part of the body. So the first option is stage 0, the second option is the stage 1, third option is the stage 2, and the fourth option is the stage 3, and the last option is the stage 4. So which stage is considered distant metastatic cancer, meaning cancer has spread to other organs or parts of the body? So please go through the question carefully and then try to give the answer, but at least try.
Ma'am, I think it's stage 4.
Please try to give the answer.
Stage 4.
Yes, the right option is stage 4. So the next question is, dash is a screening test for breast cancer. So what is the name of the screening test for breast cancer?
Mammogram.
Yes, the mammography. Yes. Next question is, the biosensor with the interdigited electrode was to understand the dash property of the tissue. The biosensor with interdigited electrode was to understand the dash property of the tissue. Santosh, what is the right answer? Try now.
Ma'am, I don't know, ma'am.
The electrical property of the tissue.
Okay,
Electromechanical.
ma'am.
Next, the question is the question number 15 is, for patterning the chromium and gold, which process we have to follow? So I think I have already discussed about it. So I need the answer. I think you will give the answer. How to deposit or patterning the chromium gold? Patterning means I am talking about the lithography process.
Ma'am, photoresist.
Yes.
Positive photoresist.
Like, at first we will deposit the chromium and gold, then when the chromium gold, we will deposit the positive photoresist, then after that what process we will follow?
Oxidation.
No, not oxidation. I am talking about the photolithography stage.
Etching process.
Before etching we have to pattern transfer from the mask to the photoresist layer. So how we will transfer that pattern? I have already discussed in this class how to transfer this uh, pattern from the mask to the photoresist layer. So which process we will follow?
Lithography process.
Okay, lithography process, but in which step? Like you have coated the wafer with this, like after the deposition of chromium gold, you have coated the wafer with this positive or negative photoresist. Then we will follow which process, like which step? We will go for the soft bake
Soft
process,
bake.
because
Soft
hello,
baking for
hello.
yeah, we'll go for soft baking. I think we will place it for at 90 degrees Celsius
Okay.
for 1 minute.
Yes.
Is
Then
and then after that bright field mask. Sorry, once that is done, then we go for um,
then we go
one
for which
second.
process?
Bright field mask. I mean
Okay, we will load the mask. Then
mask.
after
Right.
mask loading, which process we will flow?
UV light.
Or
I
it
mean,
will,
we expose.
it actually it is called a UV expose.
Yeah, UV
Okay.
exposure.
Yeah. Then
I think after that we'll go for hard bake,
okay.
which is 120 degrees Celsius for 1 minute.
Actually, before the hard bake process, now we are going to follow the developing process. After the developing
Developer,
process,
a developer, right? You are going to
yes,
keep it in developer.
yes.
Acetone.
No, actually, for
Sorry, sorry.
developing solution, we have to use
Okay.
some developing solution is there. So according to the positive photoresist or negative photoresist is used, when actually can you tell me what is the difference between the positive and negative photoresist?
In positive photoresist, the one which is exposed will be uh, one which is exposed will have a more. I mean. In positive, it will be a reverse of what we do, right? In positive photo or negative
When a
photoresist.
positive photoresist is used, in that case the exposed portion become weaker or harder.
The exposure portion will be harder actually, not
No,
weaker.
it will become
Yeah,
uh,
reverse. Positive will
actually
become weaker
when we
and
use the positive photoresist, now in that case if there is a mask is present, so the mask, there is a chrome pattern is there in the mask, and below there is a substrate, or where the positive or negative photoresist is coated. If it is positive photoresist, when you go for the UV expose, and then there is a chromium pattern is there, so it the covered portion is there, the covered portion, it is not coming direct contact with the UV light, and the transparent area of the mask where the UV light is coming directly, and the positive or negative photoresist is coming direct contact with that UV light. Okay, and when the UV light is coming direct contact with that portion, if it is positive photoresist, it is become weaker. So when we go for the development process, we dip the wafer into the developing solution. In that case, the weaker portion which is coming direct contact with the UV light, it will gone, and the remaining positive photoresist will stay on that on the surface of that device or the substrate. And after that, and negative photoresist, the opposite is happening, the exposed portion become more harder, or in the unexposed portion which is covered, it will become weaker. Okay,
okay.
and after that, After the development process, which process we will following?
Hard bake, ma'am.
Yes, hard bake. And what is the temperature and time?
120 degrees Celsius and
1 minute.
yes, ma'am.
Okay. So after the development process,
Hard bake will be.
yes, hard bake. After hard bake,
We have to etch the substrate.
yes,
Etching,
we
ma'am.
have to etch the deposited material. Like if it is chromium and gold, now. So first we deposited the chromium, then over this chromium we deposited the gold. So when in the front side we want to etch this chromium gold, so first we have to etch the gold, then below the chromium. So first we will use the gold agent, then we will use the chromium agent. Okay. And after the etching process, which process we will follow?
And finally, we have to etch with acetone to remove the strip of the photoresist developer.
Yes. Now the next question is how to fabricate a chip for cancer
Previous
diagnosis.
question. Ma'am, previous question. Answer, ma'am. The whole process is the answer for this, right?
Yes.
Okay, ma'am.
Like how you will transfer the pattern. It's when pattern transferring of this chromium gold. So you can discuss about this all the process. And the next question is how to fabricate a chip for cancer diagnosis. It is similar to the pressure sensor, whatever we have discussed earlier, the pressure sensor, but there is an extra portion, some tip is present.
VOC, volatile organic compounds, can be used.
How to fabricate the chip for
Okay.
cancer? The fabrication process I'm asking about. And it is similar to the piezoelectric pressure sensor. Like if we put a cancer tissue on the device, in that case we will measure the elasticity or the resistivity, how much resistivity or elasticity change in that devices. Okay, in that for the cell, how much resistivity or elasticity changes. So how to fabricate this type of sensor or this type of chip? There is no hurry, you can take your time and then we will discuss. It is the same way to fabricate, how you fabricate the piezoelectric pressure sensor. I have already discussed in this class.
Yes, ma'am. It is fabricated like a diaphragm. We use anisotropic etching.
Okay. And then
And then we manufacture, we make the top of the substrate two contact pads.
first actually there is a like substrate, then there is a silicon dioxide layer, because we can't deposit the electrodes on directly on the silicon wafer. That's why we need the silicon dioxide wafer. So on that silicon dioxide wafer, we have to at first deposited some of the contact layer, like the gold or chromium gold layer. Then we will follow the photolithography process, like at first we discussed earlier how to patterning or how to transfer the chromium gold. So this is the wafer fabrication process to fabricate this ID pattern or interdigited electrode pattern, the chromium gold pattern. So at first the silicon wafer is present, then silicon dioxide is present, then after that after that on the silicon dioxide layer we have to deposit the chromium gold for the ID pattern or interdigited electrode. We have to prepare the electrode now, and if we need the micro heater, like if for the cancer cell diagnosis, actually we maintain the 37-degree temperature now. So in that case we have to fabricate a micro heater on that. So first we can deposit the nichrome, so and we go through the photolithography step, and using this photolithography step this micro heater is fabricated. After that the silicon dioxide or oxide layer is we have to grow. Then we can grow the like this ID pattern. Because why we need this silicon dioxide layer in between this ID pattern and micro heater? Because in ID pattern is also metal, and also the micro heater also the nichrome it can conduct. So there is a electrical shorting can be happen. That's why to stop this electrical shorting we are using the a dielectric layer or the oxide layer in between this ID pattern and the nichrome and the micro heater. So after that what we have to do, we have that piezo resistive or the piezo resistive material where we put the sample or this cancer based cell. So the okay, you can go. Okay.
Thank you, ma'am.
And what happened in that case, after that the piezoelectric material is deposited and it is patterned, and after that what happened in the back side also you can you have to etch. Actually we have to make a diaphragm type, so there is a pressure in that portion so it can bend. So how much bending is happening, so we can calculate how much change in the resistance of this device. So like this way we have to etch from the back side. So what process we will follow? Can anyone tell? If you want to, yes, etching process. Which etching process we will use?
Sorry?
Which etching process we will use? What type of etching process is present?
Acid etching?
No, actually I am asking about the dry etching and wet etching process, as isotropic and anisotropic etching process.
It's a wet etching.
Yes. And what is the difference between anisotropic and isotropic etching?
Where solution is used for isotropic.
For anisotropic also we can use no solution.
No, I have no clear idea about it.
Okay, Shubhendu, I think I have already discussed in this class, so can you explain? Shubhendu?
No idea.
I have already discussed now the anisotropic etching and the isotropic etching process. In isotropic etching process, when you dip the wafer into the chemical, it will etch the wafer in all direction. And but if we go through the anisotropic etching process, what happen in a particular direction it will etch the wafer. Okay. So if we want that type of shape in a particular direction, it is etching, so it is called anisotropic. But what happens for isotropic, it is in all direction it will etch out. So it is clear to you?
Yeah.
Okay. Then yes, after that we can fabricate. So in the back side we will etch the silicon wafer. So can you tell me the name of any etching process which is used for etching the silicon wafer? The solution name or
Acetone can be used.
no, actually acetone is used to remove the photoresist.
Oh, photoresist.
Take your time, but at least try. Which etching process or chemical is used to etch the silicon wafer?
KOH.
Yes, KOH solution we can use, and also the TIMA process is used. TIMA solution is used. Okay.
Okay.
Okay. So and the additional way you can fabricate the sensor chip for cancer diagnosis. So in the front side where the piezoresistive material is present, in there you can deposit the silicon dioxide, and on the silicon dioxide you can deposit the gold electrode, and on the gold electrode you can deposit or you can deposit the SU weight material. So SU weight tip, so it acts as a SU weight tip. So like this way, like this is the back side portion, and the front side, what the back side portion you have etched the silicon wafer and you make the diaphragm type portion, and in the front side what is present, at first the silicon dioxide, then what present after the silicon dioxide you have yes, are you telling something?
No.
Okay, so after the silicon dioxide the micro heater is present. After the micro heater, to stop the electrical shorting, what we have done, we have deposited the silicon dioxide or oxide layer, or to stop the electrical shorting. Then we have to deposit the ID pattern. After the ID pattern, we have to deposit the piezoresistive material. After that we have to deposit again the silicon dioxide and then gold, because in piezoresistive materials gold directly can't be deposited because it is not adhesive in nature. So in that case silicon dioxide is deposited, then the gold electrode is present, and after the gold plate the SU8 tip is used, or SU8 is deposited. Like that way the this is the fabrication process of a chip for cancer diagnosis. Next question is, which layer is present in between the micro heater and ID electrode? I think I have already told. So interdigited electrode and micro heater, which layer or which material we have deposited to stop the electrical shorting? Yes. And the next question is, what is the difference between positive negative photoresist and AC weight in lithography process?
Yeah, as you have told already.
Actually, I have told about the positive and negative photoresist, but what is the change in the lithography process when we use the AC weight? Think and then tell, then I will explain. What is the basic difference of in the lithography process when you go for the positive and negative photoresist, and when we are going to use the SU weight. Take your time, but at least try.
Negative photoresist.
No, actually, when you use positive and negative photoresist, what happen in that case? At first, we go for the it means after the positive photoresist coating, we go for the soft bake process, which is the and the temperature of the soft bake process is 90 degrees centigrade for 1 minute. But when we deposit or when we cover the wafer with the AC bed, actually AC bed is acts as a negative photoresist. But when we coated the wafer with the AC weight, in that case the soft bake temperature is is 65 degree. There is a main difference. The soft bake process. So when we use the positive and negative photoresist, in that case the soft bake temperature is 90 degree for 1 minute. But when we deposit the AC weight, when we coated the wafer with the AC weight, then the soft bake temperature is 65 degree centigrade, and the time is depends on the thickness of the AC weight. Then what happened next? And the next change is the photolithography step is the hard bake process. So for when we use the AC weight, now in that case after the soft bake process we go for the hard bake process. And what is the temperature of the hard bake process? When we use the AC weight, the hard bake process temperature is 120 degree centigrade, and the time is depends on the thickness of the AC weight. But what happened for positive negative photoresist? After the development process we use this hard bake process, okay. But when we use the AC weight, after the soft bake process we directly go for the hard bake process. And another change is after the when we use the positive and negative photoresist, after the development process we go for the hard bake. But after when we use the AC weight, there is another baking process is there, which is where the temperature is greater than 125 degrees centigrade, and the time is also depends on the thickness of the AC weight. Okay, this is the main difference. And the next question is, the following statement is true or false? For flexible MEMS device, AC weight acts as a electrode when coated with gold. So it is true or false? So it is true. So next question is, in technical term, what is the meaning of ablation and where it is used? Do you know the answer?
Removal of some tissue.
Okay. And where it is used?
Where when you want to detect some pathological tissue.
Like in cancer treatment,
Yeah,
we
in
can
case of
use.
cancer, any disease tissue
Yes.
you want to take out, you will remove. That procedure is said to be ablation.
Yes. And this is the next question. 5 different type of 3D printed names.
One is material cities or printer.
Printer name.
Okay, fuse deposition modeling.
Okay.
Um, Metal jetting.
Okay. Stereolithography, selective laser sintering, and laminated object manufacturing.
Okay, glowing.
And The next question, in which 3D printing process the object is created by selectively curing a polymer resin layer by layer using laser beam? So where, in which process laser beam is used?
FDM, fused deposition model.
No, actually this is not the right option.
Stereolithography. That
Yes,
is for we use UV light in the
it's stereolithography. The right option is
laser.
stereolithography.
But if FDM we use UV light, right?
Okay, but here actually the main thing is in which 3D printing process the object is created by selectively curing a polymer resin layer by layer using a laser beam.
Okay.
So it is, I think, SLA. This means stereolithography. Next, which 3D printing process gives a high accuracy and a smooth surface? Actually, in the lecture video, it is discussed that the SLA is gives the high accuracy and a smooth surface.
Mm.
And the next question is, in which 3D printing process the printer selectivity sinters the particles of a polymer powder one layer at a time? Here is the clue, is the sinters. SLS is the right answer. Selective laser sintering.
SLS. Okay.
Yes. And the next question is, dash technology offer very high design freedom, high accuracy and produce parts with good and consistent mechanical properties compared to FDM and SLA.
Metal jetting.
No, actually SLS.
SLS.
Yes.
Stereolithography.
Yes, sir.
Sintering.
Sintering. And here actually the next one is the fabrication step. I think we have already discussed about the fabrication steps. And the difference between Piranha and Tima. I have already told the Tima is the etching process. So by this etching process we can etch the silicon wafer. So do you know about the Piranha?
No idea.
Piranha is a wafer cleaning process. It is a solution. It is a mixture of 3:1 ratio, the H2SO4 and H2O2. So this ratio of these chemicals we use to remove the contamination from the wafer surface. Okay, this is the wafer cleaning process. And the next question is, why annealing is required? Do you know about the annealing?
Annealing is sudden cooling of a metal.
No, actually annealing is a heat treatment. So we can
Heat
reduce
treatment.
the defects. Okay.
Okay.
And the next question is, what is the difference between contact and projection printing lithography? So there are three types of optical lithography process are present. The first one is the contact printing photolithography. The second one is the proximity, and the third one is the projection printing lithography. So what is the difference between these two types of printing lithography technique? Do you know the answer? Or I will explain. So what happened in contact printing lithography, when you go for the UV expose now, the like the photoresist and the mask, there is a mask is present now, from where the pattern is transforming to the wafer. So what happened when we go for the UV expose, the mask and the photoresist is in direct contact. So what happened in that case, there is a defects, like if you regularly use that type of mask, and so when we curing or separate this mask or the photoresist or the device, so there can be defects can present. Okay, if it is in direct contact with that mask and the photoresist. But and what happened in the projection printing? So if there is a small gap between the mask and the photoresist, which is coated on the surface substrate, so if it is a small gap between the mask and the photoresist layer, so it is called the proximity. And when it is called the projection printing, so in between the mask, here is a light, this is the mask, and this is the photoresist layer which is covered on the top surface of the substrate. So in between the mask and the photoresist layer, another lens is used. Okay, why the lens is used? To reduce the feature size. So we can fabricate, like we can transferring the pattern, whatever pattern is present on the mask now, we can reduce that size. So we can go through beyond this 2 micrometer size. Okay, so it is reducing the 10 times size, whatever mask size is present on the mask, so it can reduce it 10 times when you use this lens in between the mask and the photoresist layer. So it is called the projection printing lithography. And this is the last question. They discuss about the different CVD and PVD technique. I think I have already gone through that. So can anyone explain what is CVD and PVD technique? Dr. Surgeon? Am I audible?
Hello. Yeah.
So have you
We
yes, have you heard about the CVD and PVD?
yeah.
So
So
what
usually
is
PVD is a solid form. I mean, solid we use, and then gaseous form will be used in CVD.
gas is like carrier gas we can use, but the material not only in gaseous form, we can use the solid form. Okay.
Okay.
Okay. So different type of CVDs present, like atmospheric pressure CVD techniques, low pressure CVD techniques, and the plasma enhanced CVD techniques, and PVD techniques, the sputtering technique, the E-beam evaporation, and the thermal evaporation techniques are present. So with this question we are ending the session here. So I think this is the last
CVD.
session.
Just a minute. CVD sputtering and all comes under
PVD.
CVD.
PVD, sputtering, E-beam evaporation, and thermal evaporation. It is the part of PVD.
Physical vapor
Yes,
deposition.
physical vapor deposition. And chemical vapor deposition is atmospheric pressure chemical vapor deposition, low pressure chemical vapor deposition, and plasma enhanced chemical vapor deposition.
Okay.
Okay.
ম্যাম
Yes,
পিভিডি তো একটা কোটিং,
PVD is a technique to deposit any material. Okay. So physically,
মানে একটা লেয়ার লেয়ার টাইপের তো পিভিডিতে।
no, PVD is not a layer. Actually, PVD is a technique to deposit any material. Okay. So we are depositing. The technique is called the physical vapor deposition. This is deposition is a technique. Then using this technique, we are depositing any material or layer on the substrate. Okay. So we are ending this session here.
থ্যাংক ইউ।
You can leave. Okay.
Thank you.
Okay.
Thank you.